Hey kiddos, sorry, my video recorder cut off at 15 minutes. So this is part B of our momentum lesson. Let's continue talking about deriving the law of conservation of momentum. So again, we were setting the changes in momentum equal and opposite to each other, rearranging, and we finished where the initial momentum of the blue cart and the initial momentum of the red cart added together was equal to the mass of the blue cart times V final blue plus the mass of the red car times the velocity final red. And so what this looks like is actually mass times velocity initial blue is the initial momentum of the blue car plus the initial momentum of the red car equals, looks like the final momentum of the blue car plus the final momentum of the red car. And so it's almost like the momentum of the initial momentum of the red and blue car equals the final momentum of the red and blue car added together, where really what we're talking about is immediately before and immediately after the collision. So I like to think of this equal sign as the point at which the collision happens. So initial is right before the collision, final is right after the collision. We don't have to decide where our initial and final are. Like in the law of conservation of momentum, initial is immediately before the collision, final is immediately after the collision. And so we can then say, right, total initial momentum is equal to total final momentum. Okay, and so we can summarize that even further by just saying P initial equals P final. And just for the sake of completeness, we can put these little vector symbols here. And this is the law of conservation of momentum. All right, so I'm going to go ahead and just box this whole business here because this all are different ways of writing the law of conservation of momentum. Okay, so let's do an example. So we've got two masses, so 3 kilograms and 7 kilograms. So we can label them. You can use A and B, 1 or 2, whatever sort of subscripts that you want to. I'm going to call mass 1 3 kilograms and mass 2 7 kilograms. And they both start from rest. So they're both together, and so the initial velocity of both of them is 0. The masses are released, and they are pushed apart by a spring. So imagine we had them both at rest on the center of our track, and we press the button to deploy that little spring-loaded post, and they would then fly apart. Okay. So when the spring is fully decompressed, the 3 kilogram mass moves with a speed of 10 meters per second. So we called the 3 kilogram mass 1. And so we can say after that spring has decompressed, right, pushing on that mass 1 has a final velocity of V1 final, which is equal to 10 meters per second. we want to know the final velocity of the 7 kilogram mass, which we called mass 2. So we want to know V2 final equals what? And I want us to think about if when we did that experiment, when we were doing our collisions educational play, when we have two masses at rest on the center of a track and we press the button to deploy the spring, one of the masses goes one way and one of the masses ends up going the other way. So that means if we write the final velocity of mass 1 as a positive value, that means what we're expecting is a negative value for V2 final, indicating that they're going in the opposite directions. We don't need to put that negative in to indicate that we're expecting it. The math will naturally put the negative in there for us. So let's do momentum initial equals momentum final. And we know that both of the masses have a velocity of 0 initially, and so this initial momentum is 0. So we have 0 equals, and then the final momentum of both of them is the sum of their individual momenta added together. So mass 1 times velocity 1 final plus mass 2 times velocity 2 final. Okay, so that's our conservation of momentum equation. So we've got 0 initial momentum because neither object was moving. After we deploy the spring, both of our masses will be moving, and we can plug in our knowns here and solve for our unknowns. So we've got mass 1 is 3, velocity 1 final is 10, plus mass 2 is 7. Velocity 2 final is our unknown. Oops. That's 2 final. Okay. And so when we solve this, 3 times 10 is 30. We subtract it over here and we get negative 30 equals 7 times V2 final. Okay, and then with sig figs and all that, we can get V2 final is equal to negative 4 meters per second. And look, there is that negative sign, right? Which means mass 2 went in the opposite direction. Okay, so that's what's called an explosive collision. Okay, so let's take a pause here and I'm going to ask you to do some practice. So I would like you to try the processing momentum worksheet that's attached on the Google Classroom. You can just solve that in your notebook paper if you would like, answer those questions. Some of them are redundant. If you have any questions about any of those things, you can talk to me about them at some point. Send me a message, send me an email, or we can schedule a Google Meet. And then at the end of chapter 7 in your textbook, please try the focus on concepts numbers 1 and 2 and the problems 1, 2, and 5. All right, and again, let me know if you have any questions. We can go over some of these together when we meet next week. All right, and then please don't forget, before we meet next week, answer question number 1 on the classroom. Okay, and that's just going to be almost how I take attendance for this first meeting, just to see if you're engaging in the content that we've been talking about. Thank you so much for your patience. It's been really good to try and talk to you all. And please let me know if you need anything, if something is working, is not working. I've also posted a survey on the Google Classroom as a way of communicating with me on this first attempt, just to let me know what's good, what's bad, what can be changed, and if you need anything. All right, kiddos, stay safe. And we'll talk to you next week. Bye-bye.